Good evening, everyone. Please be seated. If any of you are new to the college's lecture series, I'd like you to know that after my talk, there will be refreshments in the corridor and then a question period in the junior common room, which is at the other end of the corridor. What is the measure of electricity? The question itself raises questions of its own, for not all things are susceptible to measure, and even when they appear to be, it is not always clear whether measure applies to them as wholes or only in certain respects. For purposes of this talk, let me propose that a measure of something must, at minimum, enable us to speak of that thing in terms of more and less. Faraday inherited an electrical vocabulary that appraised electricity as more or less in two respects. First, in quantity, and second, in intensity. At the outset of Faraday's researches, neither he nor anyone else had been able to state just what these two characteristics were, nor to explain how they related to one another. On the other hand, everybody had some rough and practical idea of them, as we may gather from Faraday's unassuming characterization in the third series. The term quantity in electricity is perhaps sufficiently definite as to sense. The term intensity is more difficult to define strictly. I am using both terms in their ordinary and accepted meaning. If Faraday regarded the term quantity as relatively straightforward, it is probably because at the time he began his researches, the conventional idiom of electrical thinking was that of electric fluid, a special kind of substance, thought to be endowed with the power to attract or repel other portions of electric fluid. Electric fluid was either vitreous, like that which could be evolved upon glass surfaces, or resinous, like that which could be produced on rubber, gum, amber, and similar materials. Portions of unlike fluids attracted one another. Portions of like fluids repelled each other. And the more fluid there was, the stronger that attraction or repulsion would be. It is easy to know what we mean by quantity if electricity is a fluid. But is it a fluid? And how can we know? In contrast, as Faraday implies, the fluid language fails to offer a similarly clear image of intensity. What can it mean for a fluid to be more or less intense? Faraday will seek, and perhaps he will find, a clearer understanding of both these terms. As the third series opens, we find Faraday in almost the same position as Socrates of the Meno. For how can we hope to know the properties of electricity unless we first know what electricity actually is? We well remember Meno's reply when Socrates asked after the what of virtue. There will be no difficulty, Socrates, in answering that. Take first the virtue of a man. It is to know how to administer the state, in which effort he will benefit his friends and injure his enemies, and will take care not to suffer injury himself. A woman's virtue may also be easily described. It is to order her house and keep what is indoors and obey her husband. Every age, every condition of life, young or old, male or female, bond or free, has a different virtue. Meno is positively exultant as he contemplates the rich variety of virtues. How disheartening is it then to consider that the electrical science of Faraday's time, though professing to seek a unitary account of electricity, can offer little more than a Meno-like catalog of electricities. These include voltaic electricity, which is evolved by devices like Alessandro Volta's cups. Faraday will study voltaic action extensively in the 7th series, and will show there its relation to chemical combining power. Magnetoelectricity, obtained through the relative motion of magnets and conductors, and which Faraday had already studied in the 1st series. Thermoelectricity, produced when the junction between two different metals is exposed to heat. Animal electricity, which is produced by several fascinating families of both freshwater and saltwater fishes. Faraday will study the wonderful electric eel in the 15th series, one of the most engaging of all his researches. And finally, common or ordinary electricity. This is what we now call static electricity, the electricity produced primarily by friction, for example, by rubbing a resinous rod with wool or a glass rod with silk. But how often do we undertake such highly specialized activities as these, except in a classroom or similarly contrived setting? In our day, there would seem to be nothing at all ordinary about the electricity that arises from friction. But I assure you that when I was a child, rugs, sofas, and especially automobile seats could easily give you a very unpleasant jolt if you carelessly walked across a carpeted room or slid out of an upholstered piece of furniture and then touched a doorknob or a water faucet. Today, many fabrics contain anti-static materials, which greatly reduce the frequency of such experiences. So for us, the terms common electricity and ordinary electricity are no longer apt, and they are consequently no longer in common use. Unfortunately, today's more familiar term, static electricity, is misleading in its own way. For many of the signs that alert us to the presence of static electricity occur precisely when that electricity is not static. Those unpleasant shocks which lurked in my family's home and automobile represented the discharge of electricity, which had previously been built up by friction. They were instances of electricity in motion, not electricity at rest. Faraday's efforts to demonstrate the identicality of this swarm of electricities occupies the first and longer part of the 3rd series. Only then does he set out upon the second part, where the topic is measure, particularly the measure of quantity. Readers may notice a distinctive suppleness in the language Faraday adopts for this discussion. While he does not reject the imagery of electric fluids outright, he never crafts his descriptions in a way that depends on that imagery. Now, one way we can estimate quantity, whether of electricity or anything that is evolved or produced, is to identify a repetitive element in the process that produces it. Then, presumably, each repetition of that action will produce an equal amount afresh. Faraday obtained common electricity from a frictional plate machine in which a large plate of glass was rotated against a fixed rubber, which was usually made of silk-wrapped leather rather than what we now call rubber. The appliance shown here is a smaller version of Faraday's enormous machine, which featured a glass plate of 50 inches diameter, nearly 4 times as large as this one. At several points in the third series, Faraday treats each turn of his machine as developing the same quantity of electricity. You can see why such a supposition is reasonable, for it is easy to make sure that all revolutions of the crank are accomplished with uniform effort and speed. And to the extent that individual turns are identical to each other, there is no obvious reason why successive turns would not produce identical results. This same-again principle of reasoning is familiar to us in other contexts, such as grinding pepper in a mill. Indeed, in the case of grinding, we are rewarded with a clear image of quantity in the form of a heap of the ground substance, as shown here. But when Faraday cranks his plate machine, no heap of electricity is produced. Is electricity even the sort of thing that possesses quantity in the sense of a heap, a pile, or a mound? Once again, we are reminded of Socrates' lament to Meno. If I do not know the what of something, how can I know the such of it? In our present case, if we do not know the what of electricity, is it really meaningful to ask the how much of it? When Faraday remarked that the term quantity was perhaps sufficiently definite as to sense, he meant to acknowledge that we habitually think of quantity through images of accumulation or gathering up. But do not overlook the note of reservation suggested by his word, perhaps. Faraday is far from confident that electricity is really amenable to such imagery. We regularly use that language for electricity without a second thought. But can we point to any body of experience that gives real content to that language? If electricity does not manifest its quantity directly in experience, might it do so indirectly? Sometimes, for example, we think it natural to express the magnitude of something in terms of the power it exercises. Galileo offers a memorable instance in the two new sciences. Segredo is speaking here. Thus a vast number of ants might carry ashore a ship laden with grain. And since experience shows us daily that one ant can easily carry 1 grain, and it is clear that the number of grains in the ship is not infinite, but falls below a certain limit, then if you take another number, 4 or 6 times as great, and if you set to work a corresponding number of ants, they will carry the grain ashore and the boat also. It is true that this will call for a prodigious number of ants. That delightful phrase, a prodigious number of ants, seems to employ the imagery of number, but its rhetorical burden is rather the sheer magnitude implied by the ability to move the grain and the boat also. The phrase expresses huge, undifferentiated totality, whose greatness is known primarily by what it can accomplish. It is an indirect representation of quantity. Frictional electricity, too, seems to express quantity only indirectly. When a rubber rod is stroked with woolen cloth, it acquires the power to attract a small ball of cork or pith. We say that the rod has been electrified or charged with electricity. And in the left-hand sketch, the electrified rod has succeeded in drawing the ball aside through a moderate angle of perhaps 9 or 10 degrees. But after receiving additional strokes with the wool, the rod is able to urge the ball to a greater angle, perhaps as much as 18 or 20 degrees, as shown on the right. Is it not reasonable to believe that the rod on the right exerts more attractive force precisely because it has acquired more electricity? But this is conjecture, not direct experience. Any notion of quantity we can gain from this experiment is limited to what we can surmise from the angle of the suspended pith ball. But angle is no image of muchness, and it shares none of the straightforwardness of such eminently legible figures as heap, mound, or, in the fluid case, puddle. If not the pith ball, then, might some other electrical instrument offer a more immediate experience of electrical quantity? The distinctive power of electrified bodies to attract or repel other electrified bodies is the principle of several electric indicators that are considerably more refined than the pith ball. Two early instruments operate on the principle of mutual repulsion. The leaves of the gold leaf electroscope, pictured here on the left, diverge from one another more or less, depending in part on how many times the rubber rod has been stroked. On the right, Henley's electrometer calls even sharper attention to angle by incorporating an obvious pointer and protractor in its design. When the instrument is mounted on the electrified conductor of a plate machine like Faraday's, the pointer is repelled from the body, just like the leaves of the electroscope. With its angular scale, the Henley instrument emphatically announces its rhetoric of numerical measurement, and hence its name electrometer rather than electroscope. But what exactly does it measure? The angle of the pointer, even when expressed numerically, still seems far removed from a direct image of quantity. In fact, one of Faraday's experiments in the third series suggests that the electrometer is better understood as indicating some other electrical attribute, an attribute rather different from quantity, though it may be related to quantity. Faraday describes that experiment in paragraph 363 of the third series. It involves an array or battery of 15 identical Leyden jars, like this one. You see that the central conductors, which are connected to the jar's inner coatings, are all joined together. Within the wooden container, the outer coatings rest upon a conductive plate that is connected to the flexible chain B, which in turn is connected to the earth. Faraday will charge these jars using the plate electrical machine. Notice the Henley electrometer mounted on the prime conductor. This was one of the chief applications of the Henley device. At first, Faraday connects only 8 of the jars, charging them by 30 turns of the plate machine. This causes the electrometer to rise to some position A. Does that position represent the quantity of electricity supplied to the jars? Certainly that quantity must be considerable, since Faraday noted that merely one revolution of the plate will, in his words, give 10 or 12 sparks from the conductors, each an inch in length. At a later stage of his experiment, Faraday charges all 15 jars, again by 30 turns of the machine. This time, he reports, The Henley's electrometer stood not quite half so high as before. Obviously, the electrometer is not measuring quantity, for the quantity of electricity was the same in both cases, the result of 30 turns of the machine. Yet with a greater number of jars, the electrometer reading was lower by more than half. What electrical characteristic was it then that the electrometer measured when it registered that striking reduction? In hopes of answering this question, let us conduct an experiment of our own. Recall that Faraday noted the generous number of sparks produced with each turn of the plate machine. This should give us pause. Why does the machine produce a series of sparks rather than one continuous spark? To study the conditions under which spark develops, I will use an electrometer of still greater refinement, one which, although invented long after the Henley device, does not differ greatly from that instrument in the essentials of its operation. The electrostatic voltmeter operates on the principle of attraction rather than repulsion. On the left is a photograph of our meter. It dates from the 1950s and is therefore calibrated in units whose defining assumptions would have had little meaning to Faraday. But we can regard the scale divisions as arbitrary units of attractive force. Let me explain this. On the right is a much simplified diagram of the meter's internal mechanism. A movable plate, B, is mounted on a pointer which pivots at C and is held in an equilibrium position by a very light spring. Plate A is fixed in place. When the plates are oppositely electrified, they attract one another, and plate B will move upward until its force of attraction is balanced by the spring. The pointer's angle of displacement then reflects the amount by which the spring has been stretched, and therefore also the force of attraction between the plates. The scale divisions are so marked as to represent broadly equal increments of that force. We will connect the electrometer's plates to a Wimshurst machine. I have separated the machine's terminals by about 1 millimeter or so. Next, I will slowly crank the machine and notice that the meter rises until a spark develops, at which point the needle suddenly falls. As I continue to crank, the meter repeatedly exhibits this pattern of rise to a maximum, followed by abrupt descent when the spark passes. The maximum is not always the same, but there always is a maximum, and the subsequent descent always coincides with the spark. The regular association between the meter's descent and the spark suggests a more pointed question. What is the condition between the terminals just before the spark passes? Whatever that condition is, it evidently results in spark each time it occurs. And since the electrometer consistently develops a maximum reading just prior to each spark, it seems very likely that the electrometer is indicating precisely that condition, which, when it reaches a certain degree, results in spark. What then is the nature of that condition? Faraday thought of the spark, and for that matter, all instances of electric discharge, as the breakdown of an antecedent state of stress in the region where the discharge takes place. Faraday calls that region, or the material which may occupy it, the dielectric. Here is his description in the 12th series. All the effects prior to the discharge are inductive, and the degree of tension which it is necessary to attain before the spark passes is therefore a very important point. It is the limit of the influence which the dielectric exerts in resisting discharge. It is a measure, consequently, of the intensity of the electric forces in activity. This golden passage finally lends imaginative content to the term intensity, which seemed so questionable to Faraday at the outset of the third series. The chief manifestation of electrical action is a condition of tension in the region between two surfaces, and that action is said to possess intensity commensurate with the degree of that tension. Intensity, then, characterizes the action. Tension, the region or material that experiences that action. The distinction between intensity and tension is a subtle but a natural one. We find a comparable distinction in two descriptions of Odysseus's great bow in Book 21 of the Odyssey. The suitor, Antinous, knows the bow in terms of its own strength, which makes stringing it so difficult. He warns the crowd, "For not easily, I think, is this polished bow to be strung." The image in this slide is that of a 5th century Theban coin. But once the bow is strung and in action, it is known by the thrum of its string, the sign of surpassing tension. And Odysseus held it in his right hand and tried the string, which sang sweetly beneath his touch. Just as Odysseus' stout bow reveals its strength through the superlative degree of tension it creates in the string, so electric action reveals its strength or intensity in the form of tension in the material between oppositely charged electrodes. Intensity and tension are two different rhetorical aspects of electrical action. Intensity characterizes the action itself, corresponding to the bow. Tension characterizes the material or region which experiences that action, analogous to the bow string. Do not underestimate the scientific importance of such metaphorical images as those of string and bow. Without them, or something like them, our understanding of natural powers would degenerate into a merely formal correlation of numbers with numbers. But any reader of Faraday quickly discovers that Faraday has little interest in symbols, whether numerical or otherwise. Faraday is constantly alert for legible images that convey the essential character of nature's beings and powers. What is so remarkable about Faraday's experimental practice is how much of it consists in allowing the phenomena to reveal their own images. Faraday's interpretation of electrical discharge as being essentially a release of antecedent tension departed sharply from the then accepted account, represented here on the left. Conventional thinking posited a buildup of opposite electric fluids on the surfaces between which spark took place. As those fluids accumulated, or so the account maintained, the inherent repulsion of like portions of fluid, combined with the mutual attraction of unlike portions, would eventually propel the electrical substances across the gap to combine with and nullify one another. Notice that the conventional view recognizes no role for the space or material between the charged surfaces. All action is ascribed to the electric fluids. Faraday's view, represented on the right, reverses the order of priority by focusing on the gap rather than the bodies which it separates, ascribing tension to the gap, but assigning no causative role to the adjoining bodies, nor to any supposed buildup of electricity upon them. If the dielectric material occupying the gap is capable of sustaining high degrees of tension, it constitutes what we call an insulator. But all known insulators, including air, have a limit to the tension they can sustain. And when this limit is exceeded, they break down, electrically speaking. The release of tension associated with that breakdown is disruptive discharge, or spark. In contrast to insulators, the materials classed as conductors are incapable of withstanding any tension at all. They break down under the slightest degree of electrical tension, and the condition of continuous breakdown under tension is how Faraday understands current in a conductor. Thus, the electrometer's pattern of rise and sudden fall in our spark experiment gives us reason to believe that the electrometer measures that very tension, or its rhetorical counterpart, intensity. How does it do so? If you recall our earlier diagram of the electrometer's inner workings, you will remember that the needle's displacement indicated the degree of extension of the internal spring, and hence the force on the moving plate, or rather, the tension in the region between the plates. But of course, the condition of the electrometer's own plates is not what we're interested in. If the electrometer is to function as a measuring instrument, the pointer's displacement must tell us about some other object, the object whose condition we wish to measure. How is that possible? Consider from the standpoint of tension, what must be the case when the electrometer plates are connected to the terminals of the Wimshurst machine? When the machine is operated, electrical tension is established in the air between its terminals D and E. I say that equal tension must therefore develop in the region between the electrometer plates A and B. For if the tensions were not equal, the conductors dA and EB would together have to bear the difference between those tensions. But recall that for Faraday, a conductor is incapable of sustaining electric tension. Thus, the tension between A and B must be equal to the tension between D and E. And the needle's displacement will therefore reflect not only the tension between the electrometer plates, but the tension between the Wimshurst terminals as well. Have we gained any fuller understanding of those troubling electrical terms, quantity and intensity? Faraday's study of the forms of electric discharge, especially spark, led to the idea of electric tension, and that image of tension, in turn, does indeed seem to offer a firmer notion of intensity, namely, the action producing a certain level of tension in a dielectric. But what about quantity? Initially, we looked to the electroscope as an indicator of quantity. But successive refinements of that instrument brought us not closer to, but farther away from the expected image. All our attempts to find in experience the imagery that a material substance would ordinarily demand, a localized heap, mound, or puddle, have led us instead back to tension. Why do the phenomena of static electricity seem to lead us so persistently away from heap imagery and toward the vocabulary of tension? Might that be a sign that tension is actually more fundamental than quantity? In fact, Faraday already has ample grounds for this view. For if electrifying a body really represents the accumulation of electric substance upon it, we ought to be able to electrify a body absolutely, that is, without relation to any other body, just as we can fill a glass with water, regardless of whether or not we fill any other container with water. But Faraday's famous cage experiment, along with other investigations, showed definitively that no body can be in a charged condition at all, except through a mediating relation with some other oppositely charged body. This means that there is no such thing as a quantity of electricity in itself. Every instance of electric charge is but one element of a mutual relation, to which Faraday gives the name induction. And in a striking passage in the 11th series, he explicitly elevates the relation over the things related. All charge is sustained by induction. All phenomena of intensity include the principle of induction. All currents involve previous intensity and therefore previous induction. Induction appears to be the essential function, both in the first development and the consequent phenomena of electricity. Furthermore, since all of what Faraday calls the phenomena of intensity involve tension in a dielectric, then it is the dielectric, not the so-called charged body, which is to be counted as the principal entity in static electricity. In Faraday's words, "In the theory of induction founded upon action of the dielectric, we have to look to the state of that body principally for the cause and determination of the effects." If the dielectric is indeed the principal entity in static electric induction, it is easy to see why Faraday devoted so much of the 11th series to studying the dielectric specifically. To that end, he designed the special inductive apparatus illustrated here. The appliance on the left is an historical reproduction. Faraday's own diagram appears on the right. Today, we would call this contrivance a spherical capacitor, but it is essentially a Leyden jar consisting of an outer and an inner conductor, with electrical connection to the inner conductor established by a conductive wire terminating at the little sphere on top. Faraday's experiments established for all time the preeminent role of the dielectric in induction. We can emulate Faraday's induction experiments. In place of his spherical capacitors, we shall use a pair of our adjustable plate capacitors, set to equal plate separations and thus electrically identical. Faraday placed his two identical inductive devices on a grounded metal work surface so that their outer conductors were permanently connected to the earth, while their inner conductors remained free. We will use a heavy copper wire for the same purpose by connecting it to the earth. The right-hand plates of our capacitors are joined to it and are thus in permanent electrical contact. The left-hand plates will be isolated from one another, except when I briefly connect them later on. To measure the electrical tension that developed when his devices were charged, Faraday employed a sensitive torsion balance, pictured here on the left. That fine instrument balanced the tension between two electrified spheres against the elastic twist of a slender thread, just as our modern electrometer, as in the diagram we saw earlier, balances the tension between two electrified plates against the elastic stretch of a spring. Both instruments, therefore, serve to measure electric tension. Faraday possessed only a single balance with which to measure both his inductive devices, but we have the luxury of using two electrometers, one for each capacitor, designated A and B respectively. Let me first outline the procedure we shall be following. Then I'll show some videos of the actual experiment. Faraday began by charging only one of his devices. Similarly, I will connect the Wimshurst machine to capacitor A alone and crank it until the electrometer approaches its full-scale reading. Capacitor A will thus sustain a definite tension indicated by the electrometer. Capacitor B, of course, will remain uncharged and will sustain no electric tension. Next, I will momentarily join the ungrounded capacitor plates. Now, think about what must happen when I do that. The joining wire is a good conductor, so it cannot sustain tension. Therefore, when contact is made, the electrical condition of both capacitors should instantly change to make their respective tensions equal, and we should expect both electrometers to read the same. That will constitute the first part of our experiment. So now, let us carry out the steps I just described. The copper wire on the left is connecting capacitor A to the Wimshurst machine. Now I am cranking the machine, and you can see the electrometer rise almost its full scale. I'm sorry, I went too quickly. But if I hadn't pressed too quickly, you would have seen the electrometer rise to full scale. Here is a close-up view of the electrometer. It shows that capacitor A is sustaining a tension of 2.80 units. I could not fit the second electrometer into this view, but it reads 0, as of course it must, since capacitor B was not charged. Now I join the capacitors momentarily, and the tension of capacitor A falls. We'll take a close-up look at the electrometer to see its new value. The tension in capacitor A has fallen to 1.37 units, while the tension in capacitor B has risen to the same amount, as it must, though again, I could not include both meters in the same view. Now, this change in tension took place when I allowed capacitor A to share its electricity with capacitor B. But since the capacitors are identical, they divide that electricity equally, so that each capacitor must now embrace half the quantity of electricity that resided originally in capacitor A alone. And the tension in both capacitors is 1.37 units. That is almost exactly half the initial tension of 2.80 units. Thus, as the quantity of electricity in capacitor A diminished by half, so too its tension diminished by half. Evidently, tension is here proportional to quantity. But doesn't this contradict what we saw in the third series? For there, when Faraday charged first 8 Leyden jars and then 15 with the same quantity of electricity, his Henle electrometer gave 2 different readings. And obviously, if one magnitude can take on two different values while the other remains unchanged, those magnitudes cannot be proportional. This reasoning, though, overlooks a critical difference between the two experiments. In the third series, Faraday was comparing the tension of a fixed quantity of electricity distributed first over 8 jars and then over 15 jars, as illustrated here. The electrometer readings are indeed very different, just as Faraday had reported. But our experiment, like Faraday's in the 11th series, compares the tension of different quantities of electricity in one and the same capacitor. The two experiments are not comparable because in the earlier exercise, the physical environment underwent significant change from a smaller number to a greater number of jars, while in the latter experiment, the environment did not change. The electrometer measured the variation of tension in one and the same capacitor. Clearly, the physical environment affects how much tension a given quantity of electricity will develop. This should not surprise us, as that environment includes the dielectric. And we have already seen how central is the role of the dielectric, according to Faraday's thinking. The next step in Faraday's experiment, and in ours, will confirm that central role by showing that different dielectric materials develop specifically different tensions. Faraday filled the airspace in one of his devices with various substances, and we shall do the same to our capacitor B by inserting a sheet of glass between its plates. Then we will run through the same experimental sequence as before, but remember that this time our capacitors will no longer be identical. You see, I have mounted a glass sheet between the plates of capacitor B. And again, we connect capacitor A to the Wimshurst machine and charge it to an initial tension. Its electrometer reads 2.83 units, nearly the same as before, while, of course, the other electrometer continues to read 0. I briefly join the two capacitors together, and the electrometers once more display equal deflections, as they must, since the tensions have to be equal. But notice that this time, the tension is not equal to half the original tension. Instead, the tension is only 1.02 units, roughly 1/3 of the initial tension. How shall we understand this? When Faraday obtained a similar result with his spherical capacitors, he concluded that the apparatus containing a solid dielectric had, in his words, a greater aptness or capacity for induction than the apparatus whose dielectric was air. To see what he means by this phrase, let us analyze our results in the same way Faraday interpreted his. When I joined the two devices, the charged capacitor gave some of its electricity to the uncharged capacitor. Specifically, the capacitor with air dielectric lost a certain quantity of electricity, and its tension decreased by 1.81 units. The capacitor with glass dielectric gained that same quantity of electricity, but its tension increased by only 1.02 units, a much smaller amount. Thus, one and the same quantity of electricity is associated with lower tension when the dielectric is glass, and higher tension when the dielectric is air. Evidently, then, Greater capacity for induction means the ability to sustain the same quantity of electricity at lower tension. Or, equivalently, it denotes the ability to sustain a greater quantity of electricity at the same tension. We could go on, as Faraday does, to show that a dielectric's capacity for induction depends on its dimensions as well as its specific material. But the main point is clear. Where static electricity is concerned, our only access to electrical quantity is through the measurement of tension. And even then, we have to take account of the medium's capacity for induction. Therefore, we must regard electrical quantity as only an alternative rhetorical expression for tension, a special figure of speech. Recall Faraday's earlier remark that we have to look principally to the state of the dielectric for the determination of the electric effects. In contrast, he described the supposedly charged conductors in this almost dismissive way. The conductors may be considered as the termini of the inductive action. Charged bodies, then, are merely the boundaries of electrical action, not its cause. To say that a body is charged no longer labels it as the source of electrical effects, but merely the place where a medium that does sustain tension switches to a medium that does not. With this characterization, Faraday has effectively turned the conventional order of causal priority on its head. Charge is no longer prior to tension. Rather, tension is prior to charge. Whatever else this may mean, it fatally undercuts the notion that charge is the name of an electrical substance. For, to use an Aristotelian formulation that would have been quite foreign to Faraday, how can a non-substance be prior to a substance? I hope I have conveyed how thoroughly Faraday's account of electricity inverted the conventional understanding. At the same time, I hope it is clear that Faraday did not arrive at his unorthodox view through polemic or disputation. He did not marshal evidence so as to refute the established conceptual scheme. In fact, at least in the experimental researches, Faraday hardly ever engages in collecting evidence, any more than he engages in symbolic mathematics. Instead, he looks directly to nature showing itself. Classic doctrines of scientific method emphasize putting hypotheses and conjectures to the test, establishing a preponderance of evidence for or against them. Such an approach is suited to an alien world, a world indifferent to human understanding, a world in which, as has been said, nature loves to hide. Faraday's world, on the contrary, shows itself in forms that may challenge our understanding, but they are not incommensurable with it. Faraday's science flourishes in a world that is fit for us, a world that is preeminently knowable. How did Faraday manage to nourish a scientific outlook so little influenced by conventional scientific doctrine? A customary answer to this question singles out Faraday's lack of a conventional education. To be sure, Faraday had little formal education and was largely self-taught. But the materials of his self-education were steeped in established knowledge. As a bookbinder's apprentice, he read volumes of the Encyclopedia Britannica while engaged in binding them. By his own account, he benefited greatly from Jane Marcet's Conversations in Chemistry, a lovely book which, however, reliably held to established and accepted teachings. Through the generosity of a friend of his employer, Faraday was able to attend lectures by Humphrey Davy, an establishment figure in science, if there ever was one. I do not think it was ignorance of established science that explains Faraday's relative indifference to it. Much of his practice in reading the book of nature points instead to his religious tradition. Faraday belonged to a very small Christian denomination, the Sandemanians, a dissenting offshoot of the Church of Scotland. Sandemanians eschewed theology and had no established clergy. Instead, the Bible was the central source of guidance in every aspect of their lives. Reading the Bible demanded no special credentials, for it was written in human language for the sake of human understanding. Similarly, they saw the natural world as having been created as a gift and a fitting home for mankind. Like the biblical text itself, the created world was seen as a channel of God's communication with the human race. You can see how such views concerning nature could inform Faraday's methods of natural investigation. If natural phenomena show themselves in terms we can grasp, they will not need to be expressed mathematically, or for that matter, through any other external symbology. We see from Faraday's own example that the study of nature requires patient and prolonged labor. But much of that labor stems not from nature's recalcitrance, but from our own sluggishness to put aside familiar thought patterns, what Faraday once called mental inertia, and allow the phenomena to speak to us directly. For Faraday, at least, the means for cultivating an ear for nature's dialect and an eye for its forms are practical rather than analytical. Before he asks questions in speech, he asks them in practice. Such are Faraday's experiments. Nevertheless, while Faraday's mode of experimenting clearly reflects central elements of the Sandemanian outlook, it would be a mistake to see him only as dutifully putting the Sandemanian creed into action. Faraday just doesn't write as though he were feeling the weight of doctrinal obligation. His prose, both in his laboratory diary and in the published researches, is simply too fresh, too lively, too responsive to what just happened. There is a palpable difference between being open to nature and observing a code of being open to nature. I invite you to think about that difference, the difference between responsiveness and responsibility, and how it plays out in consciousness and in speech. But for now, let us return to the terms quantity and intensity, the two candidates for electrical measure. For as regards their lucidity, I think we will have to acknowledge that the terms have effectively exchanged places. The term intensity, which Faraday initially found more difficult to define, has gained considerable clarity since Faraday has been able to assimilate to it the figures of speech associated with tension, and we may now understand electrical intensity as commensurate with the degree of tension developed in a specified region. But the term quantity, which Faraday previously thought sufficiently definite as to sense, has instead become highly questionable. For the definite sense of that term rested on the image of heaping up or accumulation of electrical substance, and we have seen how that image has repeatedly failed to find any grounding in experience. Moreover, now that Faraday has identified the primary electrical entity as being the dielectric under tension, not the so-called charged body, any idea of quantity of electrical substance can only be regarded as a merely verbal one, a figure of speech. Under such circumstances, would it not behoove any responsible thinker to avoid the term quantity of electricity altogether? And yet Faraday continues to speak of quantity of electricity throughout the remainder of the 11th series, and in the 12th, 13th, and 15th series. Why would he do this? Faraday nowhere speaks directly to that question as regards electrical terminology, but he does address a similar one in connection with the language of atoms. Some of you have read, and some of you will read, his 1844 paper, A Speculation Touching Electric Conduction and the Nature of Matter. In that essay, after having reviewed his many reservations about the theory of atoms, and hence also the atomic language that takes their existence for granted, he nevertheless admits, "I feel myself constrained, for the present hypothetically, to admit them," that is, atoms, "and cannot do without them." Here, then, is another instance where Faraday feels obliged to make at least provisional use of a terminology that has not been grounded in experience. A doctrinaire purist would have avoided such a compromise, but Faraday's openness extends to language as well as to phenomena, for each of these must evolve along with the other. Natural phenomena show themselves in forms and images that human beings can apprehend. And those images continually try to shape a language that is anchored in the phenomena. But such a language requires discovery, interpretation, and adeptness. And these in turn require time, patience, and love. As we do not expect to take in a dialogue or a drama on first reading, we must not expect to perform experiments once only and then set them aside. We must live with them, enter into them, and try them again and again. The idea is less to get the right answer than to capture the right idiom. The book of nature deserves multiple readings, and no two of those readings are likely to be quite the same. Thank you.